Alright, welcome back guys. We're starting chapter 4 with this section. This is section 4.1 and it's on what are called probability distributions. More specifically guys, we're really just going to be looking at discrete probability distributions, and we'll talk more about what that means here in a minute. But this chapter only has 2 sections in it, okay? So when we say probability distribution, what that actually means is how is the probability distributed, okay? So we know that to each outcome there's going to be a specific probability associated with it. So it's an actual distribution of probability. So it's very similar to a histogram, okay? And a histogram typically shows the frequency of data in a certain class, or these probability distributions, they're going to show the actual probability associated with each specific event or each specific outcome in a sample space. Alright, so let's go over these learning objectives. We're going to look at the difference between what's called a discrete random variable versus a continuous random variable. Okay, so we're going to be using x again for our variable, and then how to construct and graph a discrete probability distribution. So these are going to look more like histograms, and then how to determine whether a distribution is actually that of a probability distribution. And then furthermore, we're going to look at how to find the mean, variance, and standard deviation of a discrete probability distribution. What this means is like, what's the center of that probability distribution, and furthermore, how spread out is that probability distribution. And then finally, how to find the expected value of our probability distribution. Okay. So the expected value is something like, it's sort of like what outcome is most likely to occur based on the associated probabilities. Okay. All right, so let's talk about what an actual random variable is. So we know a variable is just a letter or symbol that we use to represent something. So I think for the most part we're going to be using x. So a random variable x represents a value associated with each outcome of a probability experiment. Okay. So a random variable, I'll give you an example. It could represent the number that comes up when you roll a die. Okay. It could be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So the variable in that specific example could take on a value of 6 different numbers, and then associated with each of those numbers that the variable assumes, there will be an associated probability. Okay, so if we're just talking about rolling a die, you know the associated probability with all of those outcomes is just 1/6, 1/6, 1/6, 1/6, etc. Okay. Now let's talk about, there's 2 types of random variables. One random variable will measure or represent values of something that is discrete, okay? Or in other words, has a finite or countable number of possible outcomes. So for example, back to the rolling the die, there's 6 total outcomes, so there's 6 discrete outcomes there. Here's another example though right here. It says the number of calls you make in a day is a discrete random variable, since it can be counted, because we're counting the number of calls, so it could be 0, or it could be 1 phone call, or it could be 2 phone calls, etc. And then if you were to graph those potential values of the random variable, they would just be points on a number line, okay, as you can see here. And so the values of x, in this case, that counts the number of calls made in a day, it can be any whole number from 0 on to infinity, I guess. Theoretically, yes, but practically, no. And then let's contrast this with a continuous random variable. So a random variable that is continuous is actually measuring or assuming values along a continuum, so not in discrete intervals. It has an uncountable number of possible outcomes. And this can be represented as a continuum or an interval on a number line. So here's a nice example. The hours per day that you spend on these phone calls would be a continuous random variable, since it can assume any number between 0 and 24, okay? So if you made 0 phone calls, then the value of this random variable, the time of that phone call, would be 0. But if you, let's say, for example, you made 1 phone call and you talked to that individual for 24 hours straight, then that would be the maximum value that continuous random variable could assume. But depending on the duration of those phone calls, it could be any number in here, okay? So it's an entire continuum, so it's not just discrete numbers. So it's not like you make a phone call and you can only talk for 1 minute, or you can only talk for 2 minutes. And anyway, on a number line, it would look like this. It would basically be this entire interval right here, ranging from 0 all the way up to 24. Okay, so x could be any value between and including 0 and 24 for this particular example. Okay. All right, so the first thing we're going to do, we're going to be given a random variable, the values that it will assume, and we will determine whether that is a discrete or a continuous random variable. All right, so number 1, and I'm not sure why I didn't leave much of a space between 2 and 3 here, but anyway, number 1, it says, let's let x, the random variable x, represent the number of Fortune 500 companies that lost money in the previous year. Well, guys, the number of companies that lost money, this is going to be countable, okay? It could be 0, it could be 1, it could be 2. It cannot be something like 1.5 or 1.3333 repeating forever. These are discrete values because we're talking about companies themselves. So this would be an example of a discrete random variable. Okay. And then number 2, it says, let's let x represent the volume of gasoline in a 21-gallon tank. Well, if it's a 21-gallon tank, it holds up to 21 gallons. So it could have anywhere from 0 gallons of gas in it all the way up to 21. Okay? So we are talking about an interval here, or a continuum. Okay? It could hold any number of gallons in between these two endpoints. So this is an example of a continuous random variable. And guys, also think about when you go to pump your gas, you rarely ever, I mean, unless you do it deliberately, but if you just go and fill the gas tank until the pump cuts off, rarely, if ever, are you going to get a discrete value. It's usually always going to be some decimal, right? Some fraction of a gallon. All right, and then number 3 says, let x represent the speed of a rocket. Well, a rocket's speed can vary, and it can vary along a continuum, okay? So its slowest speed, I guess, could be 0 if it's stationary, and then its highest speed, whatever the maximum speed for that rocket is. But the actual speed of that rocket could be anywhere within that continuum. So that would be another example of a continuous random variable. And then finally, number 4, let's let x represent the number that occurs when a fair-sided or a fair 6-sided die is tossed. Well, this is discrete, okay, because we discussed this example previously. There's a discrete number of outcomes when you toss a die, or toss or roll, whatever. Okay. So anyway, that's the difference between a discrete versus a continuous random variable. And in this particular chapter, we're only going to be considering discrete random variables. Okay. All right, so let's start talking now about a discrete probability distribution. So what this does is it lists each possible value that the random variable can assume. And then corresponding to each of those values, it lists its corresponding probability. So for example, the probability that x is equal to 1 is 1/6 when you're tossing a die. The probability that x is equal to 2 is 1 out of 6. The probability that x is equal to 3 is 1 out of 6, etc. Okay? And then it goes on to say that a discrete probability distribution must satisfy these conditions. And these should make sense intuitively. We've already talked about them in a sense. It says the probability of each value of the discrete random variable is going to be between 0 and 1. Okay, because we know the probability of any event is between 0 and 1, and that's what a value, a specific value for the variable represents a specific event. Okay, or in other words, mathematically, the probability has to be within and including 0 and 1. Okay. And then furthermore, the sum of all the probabilities has to equal 1. And we've talked about this as well. If you have a sample space, the probability of all the outcomes that are in that sample space, if you were to add them all up, has to equal 1. Okay? Something is going to occur. Anyway, think about the rolling a die example. So the probability that x is any one of those counting numbers from 1 to 6 is, well, depending on, for x to be a specific number, that probability is going to be 1/6. But when you consider the probability associated with every single one of those numbers, and you add those probabilities up, it has to equal 1, because when you roll a die, one of those sides is going to appear, right? You're going to either get a 1, 2, 3, 4, 5, or 6. Okay. All right, so let's look at how we could construct one. And by the way, guys, I'm going to try to do this one in just one video. Okay, so if we're going to actually not destruct, but construct a discrete probability distribution, then you're going to make a frequency distribution for the possible outcomes. Okay, so we have an example right here. So these are the different values that the random variable could assume. And then the corresponding frequencies, or number of times that the random variable actually assumed that value, are these corresponding frequencies right here. Okay, let's keep going. And then we're going to find the sum of the frequencies. Okay, so what do all these frequencies add up to? We could actually go ahead and do that real quick. Probably should have already had this done. Oops. So 24 plus 33 plus 42 plus, we'll call the last two 51. Okay. All right, so we get 150. So the sum of the frequencies is equal to 150. So there's a total of 150. And then number 3, it says find the probability of each possible outcome by dividing its frequency by the sum of the frequencies. Okay, so if I want to see what the probability that my random variable x assumes a value of 1, well, it occurred 24, throughout this probability experiment, it occurred 24 times out of a total of 150. So you would divide those out, 24 divided by 150, and you're going to get a decimal. And we're going to get 0.16. Okay, so you do that for all of these, and then finally you would check that the probability, well, each of these probabilities is between 0 and 1 inclusive, and that the sum of all these probabilities is equal to 1. Now I do want to say one thing, depending on how you round, it might not come up to exactly 1, but it should be very close. Okay. Well, let's actually look at this one. It says an industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Well, I could have just read this, couldn't I? Instead of actually adding all these up. It says each individual was given a whole number score from 0 to 5, where 1 is extremely passive. That's probably what I would be. And then 5 is extremely aggressive. And then the results are given in the frequency distribution below. Okay, so these are the frequencies associated with each of the values for the random variable. And it says construct a probability distribution for the random variable x, as well as a histogram using technology, and then describe its shape. All right, well, guys, to find these probabilities, we're just going to take each frequency and divide by 150 for all of these. $30 divided by 150, I know this one, it's going to be 0.20. And then 21 divided by 150. And so let's see some of what these others will be. 33 divided by 150 is 0.22. It's nice that these decimals are terminating. 42 divided by 150 is 0.28 or 28 hundredths. And then finally, we could figure that last one out indirectly, but I'll go ahead and divide 21 by 150, and we get 14 hundredths. And guys, if you were to add these, I'm kind of looking at this real quick, this will actually add up to 1. The probability of all, or excuse me, the sum of all these probabilities is in fact equal to 1. Okay. Now what I will do using Excel is we can make a little histogram or graph for these probabilities. What I need to do here is type in the values of my random variable, which are going to be 1, 2, 3, 4, and 5. And then beside each of these, I'm going to type in the associated probabilities, which will be over here. So this is really just like making a histogram, except the heights of your bars are not going to be the frequencies, they're going to be the probabilities. But the heights will be the same relative to each other. Okay, so I'm going to type in these associated probabilities. So hopefully this is also giving you an idea of how to use Excel to do some of this stuff. Okay, now what you can do, guys, you can select both of these columns, and then you can come up here. Let me see. Data. Actually, let me maximize this. Oh, insert. Yeah, come over here to insert, and let's go to this recommended charts, and I'm going to go up here to all charts, And I'm going to click on histogram. Well, no. Now, I don't want histogram because what Excel is trying to do is it's trying to create classes. We don't have enough values for the random variable to do that, and furthermore, each value for the random variable has a distinct probability, or a discrete. Let's do this one. This one will work fine. I'm going to click OK. Here it is. Now, of course, I didn't label the axes or anything, but you can see here that for x to take on a value of 1, that associated probability would be the height of this bar, and you can see on this vertical axis it measures the respective probability. So the respective probability for x equals 1 is 16%. You can see that this bar has a height of 0.16. And you can also see that right here, 3 is actually the most likely outcome, or the most likely value for x to assume, because it has the most probability associated with it. You can see that bar is the highest. Now, as far as if we go back to our question, as far as the shape, I would call this roughly symmetric. Okay, it's roughly symmetric. And so we'll actually see this some more with discrete random variables. The values are discrete, but lots of times if you have enough values and the associated probabilities of each of those values, lots of times it can look like a standard normal distribution, okay, or a bell-shaped curve. In other words, this sort of looks like that. It just doesn't really have any tails. So anyway, let's get back to this. Okay, so we made a probability distribution, and we also made us a little histogram. Now you can do this in this calculator here as well. Anyway, let's go to number 6. Back with number 6, we might, let's just see. So it says a company tracks the number of sales new employees make each day during a probationary period. So these are going to be discrete values, right? Because you either make a sale or you don't make a sale. There's no in between. The results for one employee are given. Create a discrete probability distribution. All right, so really what's happening here is this employee has worked for several days or weeks, and the number of days in which he or she made 0 sales is 16. 19 of those days during this probationary period that the sales employee only made 1 sale that day. And then 15 of the days in that probationary period, 2 sales were made, okay, etc. So the discrete random variable here is counting the number of sales made. All right, well, we're going to do this one just like the last one. Well, the first thing we need to do is sum up these sum up these frequencies, okay? Let me show you how to do this with Excel. So let me just delete some of this other stuff. Okay, there we go. Let's go ahead and delete this data. There we go. All right, and I'm going to put these values in, okay? So the values for my discrete random variable are going to be 0, 1, 2, 3, 4. And then over here I'm going to type in the respective frequencies, which are 16, 19, 15, 21, and 11. And now what I want to do, guys, is I want to sum these frequencies because we need to know the total number of days, right, or the total number of frequencies. So you could type these individually into your calculator, or actually your calculator has a sum feature as well. But what I'm going to do, I'm going to say I'm going to let this cell equal, so punch in equals, and then I'm going to come over here, and if I don't see a sum option, well, I do. I see it right here, okay? So I'm going to go ahead and click that, and I'm going to select the columns or the cells that I want Excel to sum. So then I'll click OK, and it sums them, and it gives me a total of 82. So to find these probabilities, I'm just going to be dividing each of these by 82, okay? And I'm just going to put a ... because I'm going to let Excel do the rest of this, and I'll show you how we can do that. So what we can do in this column, these are going to be our probabilities. So I'm going to tell Excel, I'm going to say equals, and then I'm going to tell it to take this cell, 16, so I just click on it, and divide it by, so divide it by this cell right here, okay, 82. Now, I want, let me think. Well, this will work for now. All right, so I do that, and this is what I get, okay? So now I go to the next one. I click equal, and now I want Excel to take this cell and divide it by the value in this cell, which is 82 again. Okay, hit enter. And once you've done a couple of these, Excel will kind of get the idea of what's happening. So it'll take this next cell and divide it by 82. Now, to get Excel to give you the values to the rest of these, you need to highlight both of these, and then in this little square down here, you need to drag it down. Well, it didn't work. I think it's because it's 14. There we go. Now let me see if this will work. Okay, now it does. Actually, guys, what's happening here is we want Excel to take each of these cells, go down this list, dividing each of them by 82. Well, because we're using the 82 over and over and over, you can tell Excel to keep the 82 the same, or to keep the number that's in this cell the same. And you can do that by putting a $sign in front of the N and another $sign in front of the 14. By doing that, it fixes the value, okay? And so once you've done that, then you can, highlight a couple of these and then pull this down. And then Excel will take this third cell, divide it by 82, take the fourth cell, divide it by 82, take the fifth cell, divide it by 82. And these would be my respective probabilities, okay? So I'm going to go ahead and copy them down, 0.195. I'm rounding these to 3 decimal places, 0.231, keep going, 0.1, actually this last one, that 1 should be a 2, around to 3 decimal places. And then the third probability is 0.183. Okay, you just keep going. 0.256. And then finally 0.134. Okay, so this would be if we had divided each of these individually by 82. This is what you would get. And you could check these, but these should sum up to 1. Now, like I said, because I did some rounding here, when you round, guys, you chop a little bit of accuracy off of each of these numbers. So it is possible that when you add them up, they're not going to give you exactly 1. It's not just possible, it's probable. Unless it's like the previous example where your decimal is actually terminated. Okay. All right, but know that you can still do this by hand if you want. I'm just trying to familiarize you with some other technology. All right, now let's answer some of these questions. So, what is the probability that on any given random day during this probationary period, the employee made 1 or 2 sales? That's the first part of the question. Then 2 or more sales. And then the third question is at most 3 sales. Okay. So 1 or 2 sales, what we're asking here is the probability that x equals 1 or x equals 2. So this is where we employ the addition rule, if you remember when we were talking about a union of 2 events. So this would be equal to the probability that x is equal to 1 plus the probability that x is equal to 2. And because we've got those probabilities right here, the probability that x is equal to 1 is 0.232 plus the probability that x is equal to 2 is 0.183. Okay, and then I guess I'll add these real quick in this calculator. Alright, so we get about 0.415. So that would be the probability that during this probationary period, the probability that on any randomly selected day during this probationary period, that the employee made either 1 or 2 sales for that particular random day. Okay. All right. What about this next one? The probability that 2 or more sales were made. Well, essentially, what we're asking here is, what's the probability that x has a value that's greater than or equal to 2? And so for this one, guys, you're using the addition principle again. This would be the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. Okay. I'm not going to write out all these probabilities. You can just look in your table here and add them up in your calculator. So that's what I'll do. Try to save us some time. And then finally, here we get a total of 0.573. Okay. And then finally, the probability that the employee made at most 3 sales. So at most 3, what that means is 0, 1, 2, or 3. Okay, so for this last one, you're going to add up all 4 of these. Or you could do it another way. Let me write this. So a probability that, well, you would write it like this, that x is less than or equal to 3. So this would be the probability that x is equal to 0 plus probability that x is equal to 1 plus probability that, already starting to skip notation here, x is equal to 2 plus the probability that x is equal to 3. Okay, so you could add all 4 of these numbers up, and that'll give you the answer. Or an alternative approach, and the one that I'm actually going to do, is use the idea of the complement. Okay, so the probability that x is less than or equal to 3 would be the same as 1 minus the probability that x is equal to 4, because these would be like mutually exclusive events. Okay, so that's the way I'm going to do it. I'm going to say 1 minus the probability that x is equal to 4, which is 0.134, and that'll give me the probability that x is equal to any of these other values from 0 to 3. So I think that's easier. So I'm going to get 0.866. Okay, guys, when you're doing your homework, if it tells you to round these probabilities, make sure you pay attention to that. Okay, that's very important. If I need these answers down, the probabilities associated with these events down here to be accurate to 3 decimal places, I probably should have rounded these to 4 decimal places. Okay, but anyway, you get the idea. All right, and then it says verify that the distribution. Oh, this is an unrelated problem. I'm sorry. This is example 7. Okay. So example 7, it says verify that the distribution. You know what? I think before I do this, I'm going to show you how you could make a probability distribution in your calculator. Just to try to be thorough, I showed you in Excel. So what you can do is come over here to Stat and go to Edit, and in list 1, I'm going to put in the values of my random variable. Just going to start typing them in. And 4. Okay, and the rest of these I'm just going to delete. And then, well, I deleted my list too. So in list 3, I'm going to plug in the corresponding probabilities. Okay, 0.195, and then 0.232, 0.183, 0.256, and then 0.134. Okay, and now I need to delete the rest of these numbers that are in that list. All right. Now what I want to do is I'm going to come over here to where it says Stat Plot. I'm going to hit second in the Y equals screen, and for number 1, I'm just going to hit Enter. And where it's got the on highlighting, I'm going to hit Enter. That means I'm turning on my stat plot. And then I'm going to come down, and I'm going to come over here to this one, because this one looks like a histogram to me. I'll click Enter. And then you want to tell the calculator which list you want it to use for the X values. Okay. Well, I put my X values, or the values of my random variable, in list 1. So I'm going to hit second and list 1. And then down here for frequency, this is the same as probability. You want to tell the calculator which list to reference to get those respective probabilities? Well, I put mine in list 3. I'm going to hit second, and I'm going to plug in list 3. And then when you've done that, if you go to graph, it will plot these. Or not plot them, but it will create your probability distribution. Now you may be wondering, well, this doesn't look like one. Why aren't we seeing bars going up and down? Well, remember the values here, guys. These are very small. So what I could do is I could come to my zoom key, and then I could come down here. Let me see. And I could go to zoom stat. What this means is that it'll zoom in accordingly with the data that you put in those two lists, okay? Specifically the probability list. So if I click enter, oh, this is still not looking like what I need it to. Let me come back over here, go into stat plot again. Well, let me come over here to the window. Let me look and see. Okay, so it's got my x's going from 0 to 8. And, oh, right here, this x scale, I don't want that to be 4. I need that to be 1. That means that I want this to go in increments of 1. Okay, so letting x be 0, then 1, then 2. Okay, not in increments of 4. That's why that was looking so weird. Now I'm going to go to the graph, and now we can see something that looks more like a typical histogram. Okay, so I don't expect you guys to know how to do this in your calculator. I just wanted to show you this. Okay. Anyway, lots of technological options for us. All right, number 7. Now what we want to do is verify that the distribution for the number of days of rain in the 3-day forecast is a probability distribution. Okay, so these are the different values that our random variable can take, and the random variable counts the number of days that it actually rained over this 3-day forecast. Okay, and it gives the respective probability for each of these. Okay, so this would have been created based on the frequencies. So this would have been created from past data in order to determine these probabilities. This would be what we refer to as using an empirical approach. Okay, not theoretical. But in any case, these are the values of our random variable, and these are their associated probabilities. Well, for this to be a probability distribution, all of those probabilities need to add up to 1. Okay, so we could type them all in here and make sure they add up to 1. And then this last one, 0.064. And hit enter. And it adds up exactly to 1. Okay. And I'm going to put in here that the sum of those probabilities is equal to 1. So to answer this question, we're going to say yes. What about number 8 here? Okay. So this is a different probability distribution. They don't actually tell us what x represents. They just give us the values of our random variable and the associated probabilities. Guys, we don't need to add any of these probabilities to know that this one is not going to be 1. And the reason is because we know that the probability of any event can never be a negative number. Okay? So this is not a probability distribution. Okay, because you remember the associated probability with an event has to be between 0 and 1 inclusive. So this one could not be. And then number 9, determine the required value of the missing probability to make the distribution a discrete probability distribution. Well, for this to be a probability distribution, all these probabilities need to add up to 1. So what we could do is add up the probabilities that we have, subtract that from 1, and that'll tell us what this last probability has to be. Okay, so you could do it like this. You say the probability that x is equal to 4 is equal to 1 minus the probability that x is equal to 3 plus the probability that x is equal to 5 plus the probability that x is equal to 6. So let's do this in the calculator. 0.33 plus 0.22 plus 0.19. Now I'm going to say 1 minus that value. Well, that one we probably could have just looked at, but anyway, we're going to end up getting 0.26. So that's what that missing probability has to be in order for this to be a probability distribution. Okay? All right. So the last thing, well, almost the last thing we're going to do is, so if we have this random variable, and to each value of that random variable there is an associated probability, then the question becomes, what would the average value of the random variable be? Okay, and the way you do that, so the mean, or mu, is you multiply each value for the random variable by its respective probability and add it to the next value of the random variable multiplied by its respective probability. And you just keep doing that and summing those, and that will give you the average. Guys, this is very similar to finding a weighted average. When you multiply each x times its respective weight, you could think about the weight as being the probability, okay? And then you added up all those products. So this is the same thing pretty much. And then to find the variance, we're going to do this step by step in this table down here. Once you know the mean, then you can take each value of the random variable, subtract the mean from it, square that value, and multiply it by that respective probability. And then add that, and then do it to the same thing, okay? So you're summing again. And then once you have the variance, to find the standard deviation, all you have to do is take the square root of it. Okay? So we're going to work this out in this table right here, and we may even get Excel to help us. So it says the number, or well, let's look at the directions. It says using the probability distribution below, so this is the actual distribution, for the number of games played in the World Series since 1903 to 2012, find the mean, variance, and standard deviation. Okay? So you know in a World Series, how many get, I'm trying to think. I can't remember how many games are played. I know in like the NBA championship, it's the best of 7. That may be, I think it's that way in Major League Baseball now, but it could be, since these records go back so far, it could have been different in the past. Okay, so anyway, these are the different outcomes. So There were some teams, evidently, in which it only took them 4 games to win the World Series. Other teams, it took them 5, other teams 6, etc., all the way to 8. And these are the respective probabilities. But again, these are based on the frequencies in which these occurred. Okay. So, but anyway, let's go ahead and write in the probabilities associated with the values of this random variable. So 0.176, 0.241, 0.213, 0.333, and finally, guys, 0.037. Okay, and then the next thing is we would actually multiply each value of the random variable by its respective probability. And that's what would give us this next column, okay? And if we sum up this column using this formula up here, that will give us the mean, okay? So we need to sum up that column, each x times its respective probability. And this is where I'm going to use technology to help us out here. And so what I actually did, guys, up here, I actually already put these values and the respective probabilities in here. So now what I can do is I can tell Excel to let's let this, well, actually I'll zoom in a little bit for you guys. Oops. Is I can tell Excel to let this cell equal this cell times this cell, which is its respective probability. Okay, I hit enter and it gives it to us. Now, since we're not using a fixed value like in that other value before, we're just using each subsequent cell times the cell beside it. After you do one of these, then you can pull this down. And Excel will assume that you're going to be using the cell below times its adjacent cell to find, wait a minute, yeah, okay. All right, so I am going to minimize this, and I'm going to plug these values into my table. All right, so 0.704, 1.205. You might be asking yourself, well, hold on a minute, why are some of these values bigger than 1? Well, these aren't probabilities. These are the values of the random variable multiplied by its respective probabilities. So it's okay if these are greater than 1. 1.278. 2.331, and then 0.296. Okay, now I need to find the sum of all these. So again, I am going to use Excel. So what I'll do is come below and I'll say, let's let this cell equal. So I'll plug my equals in there, and then the sum is already highlighted here. So I'm just going to click on it. And I'm going to drag these columns that I want Excel to sum, and click OK. And I get 5.814. Okay. So guys, this number right here, this is the average. So the mean is 5.814. Okay. So we know the mean now. Now what we need to do is, because we still have to find the variance and the standard deviation. So we need to do these other columns, because in the formula for the variance, we need to find the deviations. We need to take each random variable value and subtract from it the mean, we need to square that and then multiply it by its respective probability. And then we need to add that to the next one, okay? So we're doing this kind of piece by piece. So to find the deviations, I'm going to take each x value and subtract from it the mean that we just found right here. So again, we can use Excel to do this. I'm going to come over here though. So what I want Excel to do is take each of my, so I'm going to put equals, and I want it to take this x value and subtract from it the mean, which is this number, okay? Well, you can see that the coordinates of that cell are 07. So to fix that cell so that Excel will access this each time, I need to put a $sign in front, another $sign in between. Okay. Now if I hit enter, it'll give me this deviation. Actually, I'm going to label these. This is X, and this is P of X, the probabilities. This is X times P of X. And over here, these are the deviations. This is X minus, I have mu in here, I can't remember. How about I just write it in, X minus mu. Okay, that's actually how you spell that Greek letter. All right, now once I've done that, I should be able to just drag this down again. Yeah. And so what it does is it uses this x and subtracts from it the mean, and it goes on and uses this next value of x and subtracts from it the mean, okay, etc. So now I'm going to copy these values in my table. All right, so negative 1.814 negative 0.814. Just keep going. 0.186. We don't lack too much, guys. 1.186 and 2.186. Okay. All right, so that's this column. Now, what we do is we take these deviations and we square them. Because remember, if we just add up all the deviations, well, they won't in this case, but if you were finding the standard deviation of a data set by hand, or rather, if you were summing up all the deviations from the mean of a data set, they always add to 0, right? Because you have just as many below as above the mean. But anyway, now we need to square each of these values. So again, we can use Excel here, and what I can do is, hold on just a minute, guys. Okay, guys, so what we need to do now is we need to tell Excel to square each of these values, okay? I'm going to say, let's let this cell equal this cell raised to the second power. Yeah. Okay. And then we can just pull this down. I'm sure there's a name for this. I just don't know what it is. So this would actually be the squared deviations. Oops. Do that. Okay. Let's see. Well, I guess I'll just write it like this. I was looking for a superscript. I'll just do it like that. All right, so let's copy these down. Now you can see these, these decimals are getting longer and longer. 3.2906 around to 4 decimal places. And then zero 0.6626 0.6626. Sorry, this gets a bit unwieldy after a while. And the next one, 0.0346. And then 1.4066. Let's see. And then finally 4.7786. Okay. All right, so we got that column. Now the last thing we need to do is we need to multiply each of these squared deviations by the associated probability. Okay. This is why using technology is so nice, guys, because you're trying to do this by hand, you're copying all these numbers, it's easy to make a mistake. So now what I'm going to tell Excel to do is take this squared, well, let me come over here to equals. Let's take this squared definition, or the squared deviation, and we're going to multiply it by the respective probability, which is over here. Okay, hit enter, get that, and we should just be able to drag these down because we're not referencing a fixed cell. All right, so these numbers, these would go in this last column, and then when you sum all these up, that will be the variance. Okay. Let me just go ahead and write these out. I'll go to 4 decimal places again. 791, 5791, 0.1597, 0.0074, 0.4684. And finally 0.1768. Okay, now we're going to sum up all of these. I'm just going to put sum right there, and I'm going to use Excel again. Okay, I'm going to let this cell right here equal the sum of these cells. Okay, and so that sum is, let's go to 4 decimal places, 1.3914. Okay, so guys, that is the variance, or in other words, sigma squared, 1.3914, and so sigma itself will just be the square root of this. You can even get this in Excel as well. You could say, let's let this cell below it equal, and I think if you type in like SQ, yeah, see right here, square root RT of this cell. Well, no. Yeah. Oh, no, hold on a minute. This is not working. I think I need parentheses, and then I need to select this cell. And close those parentheses, hit enter. And yeah, now it takes the square root. So the square root, or the standard deviation sigma, in other words, is going to be 1.1796. Okay. Alright, so try to use Excel if you can, guys. Your calculator will actually do all of this stuff as well. If you come over here to y equals, oops. You need to turn this. You need to turn that plot off. Now, excuse me, if you come over here to the table, well, no, you have to go. Yeah, you have to go to y equals. Anyway, hold on a minute. Well, anyway, usually it'll show a y1, a y2. Is that right? Yeah, you can do it. You can do it with your lists. So, like, I could say up here. I then could type in what I want list 4 to be. If I want list 4 to be list 1 times list 3, then I could type that in and it'll generate this new column. So really you're doing the same thing using your calculator as you are in Excel. But anyway, if worst comes to worst, guys, you can do these manually one at a time. You just want to make sure that you probably need to carry them out at least to 3 decimal places, if not to 4, to make sure that you get the accuracy that you're going to need over here. Alright. Okay, well, the last thing is very short, the expected value. This is typically the way it's written. Capital E of X. All this means is, what is the expected value of the random variable? Well, it's the same as the mean. Okay, so the expected based on the different values of my random variable and their associated or respective probabilities, the expected number of games that it would take for a team to win the World Series based on this past data of over a century of World Series would be close to 6 games. Okay, so that's the center of the distribution essentially. It's a little bit less than 6 games. So anyway, that's what expected value means. Okay, and we just interpreted the results from that previous example. So anyway, sorry it took me so long on some of those Excel calculations, but hopefully you see the value of using Excel. And the more you use it, guys, the better you'll get. I'm actually not very good at it at all, as you can see. Okay, I can use it a little bit, but that's about it. I want to try to get better. But in any case, next section, guys, in 4.2, we're going to be looking at binomial distributions. Okay, so a binomial random variable, it's another discrete random variable. Okay, so anyway, I'll see you in section 4.2.